All right. So this is exam 2, the practice exam. Your first section is Lewis dots. So with nitrate is our first one. This 8 tells me that this is an ion of some sort. It tells me it's a polyatomic anion. It's negative. 8 tells me there's an oxygen. I know that nitrate, because you've had to memorize it, is NO3 1 minus. So our first step when doing the Lewis dot is to add together all of our electrons, our valence electrons. So using the groups, nitrogen has 5 valence electrons and each oxygen has 6. So I have a 5 from the nitrogen, and then I have 3 times 6 for the oxygens, and then a negative tells me that there's 1 additional electron from it being negative. So I have an additional 1 that I'm adding into this. So when I add this together, I get 24 valence electrons, which is 12 pairs. So I have this nitrogen that I'm going to put in the middle because out of the 2 elements, there's only 1 nitrogen, and you wouldn't put an oxygen in the middle to connect to more oxygens. You want the element with the least amount of that element, which is nitrogen. We're going to branch out our 3 oxygens, and you can do it the way I'm doing it, where I have it like trying to be equal, or you can do it like this. Both are acceptable and both will get you all the points. I'm just feeling extra, so I'm going to do it like this. So I've got 12 pairs. I just used 3 of those pairs, 1, 2, 3, to bond all of these together. So I've already used 3, leaving me with 9 left. Our first step now, our next step is to add the lone pairs to the outside. We only add to the inside if absolutely necessary. So I have 1 pair, 2, 3, 4, 5, 6, 7, 8, 9. I've used all 9. I have 0 left. I now need to check. Is everybody happy here? All of the oxygens have their octets, right? Does nitrogen? No, it only has 3 bonds. So we're going to take one of these and make a double bond. Can I take this one instead and make a double bond? Absolutely. I picked that one because I felt like it. You can pick any of these 3 bonds. It does not matter. Now we have it like this. And if this was a finished compound, then we would be done. However, it's an ion, and we need to express that. Without it, it looks like it's just NO3 as the existence of it. But it's an ion, so we need to now put brackets around the whole thing and call it negative. And that is the first one. I put this in the wrong spot, and that's okay. I didn't realize that it was supposed to be above. So this is all of my scratch work. I'm gonna take my final one and make it pretty. So we've got N in the middle with our oxygens on 3 sides. This one's got a double. See how I switched it and now I made it like this? That's just because I felt like it. I'm gonna bring it down a little bit so I can make the brackets. And it's negative, so that's my final. All right, chlorite. What do we know about chlorite? It's ClO2 1 minus for starters, I can tell you that. So now we need to find all of the valence electrons. So we know from this negative that we have a 1, so let's just add that now. We know that oxygen has 6 because of its group number, so then we have 2 of those. So we've got a 12, and then chlorine is in group 7, So it's got 7 valence electrons. So when I add this together, I get 20 or 10 pairs. So I've got 10, and this is ClO2. So I'm gonna start by putting a Cl in the middle and then connecting it to 2 oxygens. Doing that, I've already used 2 pairs. So now I have 8 left to use. I'm gonna take those and I'm gonna go 1, 2, 3, 4, or 1, 2, 3, 4, 5, 6. I've used 6 pairs. I've got 2 left. Now that I've used those 2, I can take my leftover and add them to the center atom using those final 2. Now I check if everyone's happy. This oxygen has its octet. This chlorine has 2 lone pairs and 2 bond pairs, making an octet. And this one's got its octet. The only thing missing is that we have to add that charge because it's an ion. And that makes our final. I'm gonna take it over here, take it over here. And that's my final answer. This one's a little bit trickier, and it is very likely that you will see an acid of some sort on the exam. When you have something that has oxygen in it that also has an acid, it is very important that you don't connect those hydrogens to whatever's in the middle. You connect it to the oxygens. And that's just, I'll relate back to that, but I want to put that in your head now to think about before we get to actually drawing it. So we'll start, like always, carbonic acid. That means I've got H and I've got CO3, 2 minus. When I crisscross, I get H2CO3, which is aqueous, but that's not important for a Lewis dot. So I've got 2 electrons from here. I've got 4. I've got each of these hydrogens has 1 valence electron. Each of the carbons have 4, and each of the oxygens have 6. So I've got 2 from the hydrogen, 4 from the 1 carbon, and 3 times 6 is 18, making it so we have 24 electrons. I've got 12 pairs to start working with. So just looking at this first, and we'll get to the hydrogens after. When we have CO3, we put a C, and then an O, and an O, and another O. Kind of like how we started out with the nitrate, but instead this is carbonate that we're putting in the middle. Next, I'm gonna add a hydrogen on both ends. Because like I said, we wanna add to the oxygen and not the carbon. We can't add 2 hydrogens to the carbon, then it's gonna have more than an octet, and it doesn't like that. It wants to have its 8 and call it a day. It wants to have 4 pairs or some combination of lone pairs and bonding pairs. Could I have, instead of putting it there, put it here? Absolutely. I could do it in any of the ways as long as it's bonded to oxygens, but I keep it like this because I like symmetry. So now, let's count how many pairs I've used. I'm gonna move this over here just to have more room. 1, 2, 3, 4, 5 pairs have already been used, leaving me with 7 left. I'm gonna start adding lone pairs. So I've got 1, 2, 3, 4, 5, 6, and I've got 7 that I've used. Awesome. I gotta check if everybody's happy now. Hydrogens are always happy with their 1 bond. Oxygen has 2 lone pairs and 2 bonds, making it 8. Oxygen's got the same thing going on. Carbon's only got 3. So we need to take a lone pair, and make a double bond. So I'm gonna choose the top one because I like symmetry. I'm gonna take this, make that bond, double check everyone's happy. They are. Carbon now has its 4 bonds. There's no charge because it's an acid, it's a full compound, so this gets to be my final answer. So I'm gonna take this over here and I'm gonna rewrite it. We got a C, an O, O, H, and that's that final. Next, I've got carbon tetrafluoride. Tetra means 4, right? So that means I've got F4 here. There's no mention at the beginning of anything to do with the carbon, so we can assume there's only one, making this CF4. So let's take this over here to make some room. Carbon, as we've talked about so many times, has got 4. It's got 4 valence electrons. We've got 4 for that carbon, and then those fluorines each have 7. 7 times 4 is 28. We've got 32 total. That's a lot. So we've got who in the middle? Fluorine has 4 of them, so we know we're going to want to put carbon in the middle. I'm going to branch out to all of those fluorines. This 32 gave me 16 pairs. I just used 4 of them, giving me 12 left. So I'm going to add my dots. That's 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I've used all 12. I've got to look now. Is everyone happy? Each of these fluorines have a bond and then all of their dots, and then this carbon has each of its 4 bonds. It's happy. This one is complete. Let's put our answer over here, make it nice and pretty. Always remember your lone pairs. They will dock you if you don't have them. All right, that is our first page. You've done your Lewis dots. Now we are on to the nomenclature portion, which is a very important part of each of your exams continuing forward. It is the literal building block of chemistry. You will always, unfortunately, put it flatly, you will always suffer, you will always fail if you do not get your nomenclature down. This is a great practice, and we're gonna start with this first one. So I've got calcium. What is the symbol for calcium? C, A. What is the formula for phosphate? P, O, 4, 3, minus. The charge on calcium? 2 plus. How do I know that? This is positive 1, this is positive 2, this is positive 3. It goes in a 1, a 2, and a 3. The ones over here, they kind of do the same thing, but in reverse. This is 0 because these are noble gases. They don't have charges, they're just vibing. Got negative 1, negative 2, and negative 3, and these are silly. So in the same way, this went 1, 2, 3. These went 1, 2, 3, and then they meet in the middle and do nothing. So calcium is under this +2 section, meaning it has a positive 2 charge, and you've memorized that phosphate has a 3 minus charge. We're gonna take these and crisscross them. which gets us calcium with the 3 on the bottom, saying we have 3 of them, and then we put this in parentheses to show that it's the whole thing that we have a lot of, and we have 2 of those. And that's your final answer for that one. Aluminum sulfate. Symbol for aluminum, AL. What is the charge on aluminum? Well, this 3 plus tells me the charge because it's under that thing. So we've got aluminum with a 3 plus charge, and I've got sulfate, which is SO in some combination, but it's 4, 2 minus. Same kind of deal, we're gonna take these 2 numbers, and I can literally just crisscross them like that too, if I wanted to, in which I will. I'm gonna put parentheses around this to show it's around the whole thing, get rid of the charges, put it together. That's the final. All right, for our next problem, we have copper 1 carbonate. Symbol for copper is Cu. The 1 here tells us that it's a +1 charge. Carbonate is CO3 2 minus. So when we do the crisscross on these, we take this 2 and we drag it over here, and we take the invisible 1 and we drag it over here. So when I pair these together, I end up with copper 2 carbonate, and that's my answer. Ferrous hydroxide. Now, you are not required to know ferrous by name. Fe tells me that it's iron, but I just have to double check. I'm pretty sure it's iron 2. So we're gonna take this iron, which is Fe, 2 plus, and we've got hydroxide, H and O. We've got O, H, and it's a charge of 1 minus. I'm gonna take this 2, and I put it over here, and then I take the 1, and I put it over here. Problem is, if I just put a 2 here with nothing else around it, it looks like I have 1 oxygen and 2 hydrogens. That's water. So I need to put parentheses around this OH2 when I put it together. And now that I've done that, I can put it together, and that leaves me with FeOH2, ferrous hydroxide, iron 2 hydroxide. Next, we've got nitric acid. Acid tells me something immediately, right? It starts with a hydrogen. Nitric. Ick. I ate something and it was icky. That tells me that ick goes to 8. Nitric is nitrate, which is NO3 1 minus. When I crisscross these, they have the same charge, right? So I can just cancel them out and put it together. So this is HNO3, and acids are always aqueous. Last, we have zinc bicarbonate. Zinc is Zn. The charge is always 2 plus for zinc. Bicarbonate, we know carbonate, right? We talked about her earlier. Carbonate is CO3 2 minus. But the bi tells us that we added a hydrogen, and hydrogens always have that +1 charge, so that makes that -2 a -1. It made it more positive. So this is some combination of Zn and HCO3. When I crisscross, I get a 2 over here, but like we talked about before, we need to put parentheses around this so that we know that there's not 32 oxygens, because that would be ridiculous. When I put it together, I end up with Zn, and then in parentheses, HCO3, and then a 2 on the outside of that. So it's zinc bicarbonate. The next section we have is the reverse, where we are given the formulas, and you have to write the name. So to start, this is an ionic compound, right? So I have some sort of metal with a non-metal or polyatomic. That defines an ionic compound. So I have potassium for K. So I know it starts with potassium. And when I look for K, K is not a variable charge. It's not in this section. So that tells me that I don't have to clarify whatever charge it has. So I just get to move on after writing potassium. After that, I focus on this. I hope I've given you enough time. That is thiosulfate. THIOSULFATE. And that is the answer. It's written like that. This one starts with a hydrogen and ends with aqueous. That's an acid. So it's going to be something acid. Let's focus on this SO3. SO3 is also known as sulfite. What is the rule when it comes to turning an ite into an acid? Sprite is delicious. So this is sulfurous acid. We don't call it sulfus acid, unfortunately, so it doesn't follow very easily, but it is sulfurous acid. Next, we have another ionic compound, so we're going to follow, because it's a metal and with a non-metal in this case. So we've got nickel of some kind. Nickel actually is in this section. I'm going to pause so you can find it, because I'm... Nickel is a transition metal, so it has multiple options for charges. I know that iodine has a charge of -1 because it's one of the halogens. It's over here. It's under the -1 charges. But I have 3 of them. So when I have 3 of these, I have a total of a 3- charge, meaning that I needed 3 of those. I needed 3 of these to balance this nickel, telling me that nickel has a 3 charge. We don't write it 3 like that. We write a 3 in Roman numerals. So I have nickel 3. Is it like this, or is it like this? Because it is the ion, we write it in ion form when it's the nonmetal portion. It's nickel iodide. Next we have ICl3. This one has a nonmetal to start and a nonmetal to end, meaning we have to use the prefix naming. We have 1 iodine, so I'm going to start by writing monoiodine. And since it's starting, I don't have to change this to "ide." It's only the ending. It's like a period in a sentence. We change it to "ide" when it ends. We have 3 chlorines, making it trichloride. Like tricycle. Because the iodine starts it, I can take out the mono and just call it iodine trichloride. And that can be my final answer, iodine trichloride. Next, we have cadmium and oxalate. Cadmium follows zinc in having only one charge, and that's a 2. It's got a 2 plus charge, and we know it's always a positive because it's a metal. Metals only have positive charges. So we have we have cadmium, and because it only has one charge, I don't have to write a Roman numeral for it. This is oxalate, so the answer is just cadmium oxalate. I don't have to do anything else to it. This one's a little bit more fun. If you look at it, you might say, there's no metal, so this can't be ionic. This is one of those lovely exceptions because ammonium is a polyatomic, which makes it ionic. So we have, spoiler alert, ammonium. And when we look at just this, that's phosphate. But because of this H at the beginning, it's actually monohydrogen phosphate. I'm gonna move that over because they're two different words. Some professors allow you to just write hydrogen phosphate, but both are acceptable, both are used. So that is our nomenclature section. Now we're on to everyone's favorite part, mole calculations. So this first question asks, how many moles of iron are in 33.0 grams of iron? So we are starting with iron and ending with iron. So I'm starting with grams, and I have to get to moles. Can I go straight from grams to moles? Yes, I can, because I have something called the molar mass. So I'm going to take these grams. I've got 33.0. I've got 33.0 grams of iron. And I'm going to multiply by something. I'm going to multiply by that molar mass, which we find using our handy-dandy periodic table. So iron is right here, and it's got a molar mass of 55.847. grams for every 1 mole of Fe. I'm going to plug this to my calculator, and you get, I'm going to write out the full as a larger amount of it, and we're going to figure out the sig figs together. So this number has 3 sig figs. We've got 1, 2, 3. And this number has 5 sig figs. We always use our smallest amount. So we're going to use that 3. So we're going to count 1, 2, 3. Cut it off there. This 9 tells me I'm going to round up. So our final answer for this problem is 0.591 moles of Fe. And I'm going to double check that it doesn't ask me to use scientific notation. Since it does not ask me to use scientific notation and the number is not unreasonably small or large, I can leave it like that. Do not do something that you are unsure about and put in scientific notation if you're not like 100% like I feel confident in this, because that's just more room for error and a possibility of missing a question that you actually got right and losing some points when it's unnecessary. All right, so we've got number 2 now. How many molecules of aspirin, so we're ending in molecules, contain 45.26 grams of oxygen? All right, so we're starting in grams of oxygen, and I need to end in molecules of aspirin. As we saw in the question before, I can go straight from grams to moles using the molar mass. So I'm going to go from grams of oxygen to moles of oxygen because your gateway to everything in the world is literally moles. If you do not know what you're doing, you feel stuck, go to moles because that is your gateway to every single problem in chemistry, in intro chemistry. This is the key, is to get to moles, and the rest you'll figure it out as you go. So now that I'm in moles of oxygen, I can go to moles of aspirin. I'm going to write it as a capital A because there's no A element, and that just makes my life easier. Let's take a look at our molar ratio. So in every 1 mole of aspirin, which is C9H7O4, in every mole of that compound, how many oxygens do I have? I've got 4. So on the bottom of this conversion factor or ratio that I'm using, for every 1 mole of aspirin, I have 4 moles of oxygen. So when I get to this part where I'm converting from moles of oxygen to moles of aspirin, I'm going to use this. So let's start doing that math. So I'm given the grams, which was 45.26 grams of oxygen. And I'm going to convert to moles of oxygen using the molar mass. What number am I going to use for that? 15.999. So I've got 15.999 grams of oxygen for every 1 mole of oxygen. From there, I'm going to convert to aspirin using this that we found. So on the bottom, we're going to put a part associated with the moles of oxygen. So I have 4 moles of oxygen for every 1 mole of aspirin. Now that I'm in moles of aspirin, I can go to molecules of aspirin because we've got that lovely, lovely number, Avogadro's number, which is for every 1 mole of something, I've got 6.022 times 10 to the 23 tiny things. I'm going to write tiny things because this can be associated with molecules like we're using now. It can be any sort of formula units. It can be particles. It can be atoms. It can be ions, whatever. Doesn't matter. So I've got in every 1 mole of aspirin, I'm going to put that on the bottom as well. I've got 6.022 times 10 to 23 moles of aspirin. Not moles, I apologize. Molecules of aspirin. I'm going to go back and double check that I've canceled everything out. I got rid of the grams. I got rid of the oxygen. I got rid of moles here. And I ended where I wanted to be, which is molecules of aspirin. So I'm going to go ahead and plug that into my calculator. I'm going to write, like I did in the last one, a lot of numbers. So we've got 4.258949 times 10 to the 23rd molecules. How many sig figs do I have for the first one? I've got 4. Here, I've got 5. Here, I have infinite because I counted that. That's a counting number. And this has 4 sig figs as well. So our least amount is 4. So we cut it off here, and this rounds up, making our final answer 4.2 59 times 10 to the 23 molecules. Let me move that over. Of aspirin. And that's that final answer. Number 3 also talks about aspirin. So we've got how many grams of hydrogen would be contained in a sample of aspirin that has 5.28 times 10 to the 22 atoms of carbon. So I am given atoms of carbon, and I need to get to grams of hydrogen. What did I tell you earlier? What is every chem professor ever going to tell you? You got to get to moles first. So we're going to start by going to moles of carbon, because I can use Avogadro's number for that. For moles of carbon, I can go straight to moles of hydrogen because we have a molar ratio of carbon to hydrogen within aspirin. So for that one, we have, for every 9 moles of carbon, I have 7 moles of hydrogen. And then we can go from moles to grams Y, because we've got our lovely, lovely molar mass. So we're starting with 5.28 times 10 to the 22 atoms of carbon. We've got Avogadro's number for the next part, so that's 6.022 times 10 to the 23 atoms for every 1 mole of carbon. And notice how it's atoms, because this is a single element. When it's a single element, you use atoms. If it's a compound, or if it's more than one singular element that we're talking about, it's a compound. H2, there's 2 of them. It's a compound. So now we're going to moles of hydrogen using our molar ratio that we used. So we have 9 moles of carbon, and that's going to go on the bottom to cancel out the carbon up here. And then 7 moles of hydrogen goes on the top to introduce the hydrogen. And then we're going to use our molar mass. For every 1 mole of hydrogen, we've got 1.008 grams of hydrogen. Once again, let's check that we've canceled everything out. We went from atoms to moles of carbon, moles of hydrogen, went to moles of hydrogen. We ended with those grams of hydrogen that we wanted. Now I just plug that into a calculator. We end with 0.0684535. Lowest amount of sig figs, we've got 3 sig figs here, 4 here, infinite, and 4. Our least amount is 3, so we're going to go 1, 2, 3, cut off here, making our final answer 0.0685 grams of hydrogen. The next question asks, how many atoms of oxygen are in 32 kilograms of phosphoric acid? Let's start with phosphoric acid. Ic goes to 8, so I know that this is phosphate, which is PO43 minus acid tells me that there's hydrogen. When I crisscross this, I get H3PO4 as the formula. So I am given 32 kilograms of H3PO4 aqueous, and I need to get to atoms of oxygen. Our first step is always to get into moles. However, normally when I go to moles, I go from grams to moles using the molar mass. I have to first get kilograms into grams. And that's using your handy dandy metric that you were supposed to memorize. So now that I'm in grams, I can go to moles of H3PO4. And before I get to atoms of oxygen, I have to switch from H3PO4 to O using a mole ratio, where I go from moles of H3PO4 to moles of oxygen. How many moles of oxygen is in 1 mole of H3PO4? So for every 1 mole, I've got 4 oxygens. So I'm going to write 4 moles of oxygen. So when we do this math, now that we have a plan, I start with 32 kilograms of H3PO4. For every 1 kilogram, I have 10 to the 3 grams. From there, I have to find the molar mass of phosphoric acid, which I'll do over here. So I have 3 hydrogens, 1 phosphate, 3 hydrogens, 1 phosphate, and 4 oxygens. The molar mass of hydrogen is 1.008. I have 1 phosphorus, which the molar mass is 30.974. And we have 4 oxygens, which are 15.999 grams per mole. When I total this, I get 97.994 grams per mole. And I get to have 3 decimal places because each of these had 3 decimal places. So that is the molar mass we're going to plug in next, where we have 97.994 grams for every 1 mole of phosphoric acid. From here, we're going to use this. We're going to use this next because we're doing the molar ratio to get from moles of H3PO4 to just moles of oxygen. I'm going to erase this for extra space. So we're going to put moles of H3PO4 on the bottom to cancel out. And like we said, we have 4 moles of oxygen in every 1 mole of H3PO4. And we can get to moles of oxygen to moles of atoms using that handy dandy Avogadro's number, which is for every 1 mole of oxygen, I have 6.022 times 10 to the 23 atoms. I'm going to plug this into my calculator where I get, this is the full number written out with a lot more. How many sig figs do I have? to start, I've got 2 sig figs here, infinite here. I've got a total of 5 sig figs in this one, infinite because it's a counting ratio, and this one has 4 sig figs. Our lowest number is 2, so I cut it off here and round up to 7.9 times 10 to the 24 atoms. And that is our final answer. Don't forget, it's atoms of oxygen, not just atoms. You want to clarify that. There's a chance that you could get marked down because of an error like that. All right. Number 5 asks for atoms of potassium, that's what K is, in 3.0 grams of potassium phosphate. So I have 3.0 grams of K3P, and I need to get to atoms of K. We always go to moles first, so we're going to moles of K3P. From there, I can go to moles of K using the molar ratio, that same type of thing we used over here. And then from moles of K, I can go to atoms of K using that same Avogadro's number. Now, looking at the question above, this looks pretty darn similar, doesn't it? It's the exact same pattern, you just didn't have, now you don't have to convert from kilograms to grams. We're already given grams. You'll notice with questions like this, you're following the same type of pattern, and that's kind of a continuous thing with this course. With these things, you're always going to want to convert to moles to get to your different pathways. Moles are the pathway in this class. So I've got 3.0 grams of K3P. I need to find the molar mass. So I have 3 potassiums to 1 phosphorus. The molar mass of potassium is 39.10, and I have 3 of them. And phosphorus is 30.974, and we've got 1 of those. When I add this up, I get 148.274 grams per mole. However, we only have 2 decimal places, so we cut it off after the second one, making it just 148.27. So now let's go back and plug that in. So grams will go on the bottom, which is 148.27 grams of K3P for every 1 mole of potassium phosphate. Now we are going to use the molar ratio. So for every 1 mole of K3P, how many moles of potassium do I have? I've got 3. So we're going to put 3 moles of potassium on top. And then we do our Avogadro's number because we're going from moles to atoms, which means we get to use it. So this number states that for every 1 mole of potassium, I have 6.022 times 10 to the 23 atoms of potassium. And that is our final equation. I'm going to go ahead and plug that into my calculator. So this is the full number. How many sig figs do I have? Got 2 from here, 5 here, infinite, and 4. I'm going to use that 2 because it's the smallest amount. Cut it off here. That leaves me with 3.7 because this 5 rounds it up, times 10 to the 23 atoms of potassium. And that is the first page of problems for your exam number 2. Now we are on to number 6. A 11.17 gram sample of a metal is reacted with excess oxygen to produce 15.97 grams of the oxide MO2. What is the molar mass of element M? So we are given that there are 15.97 grams of MO2 produced from 11.17 grams of a metal. So this is my total, right? And this is the metal part. So if I take out the metal, all I have left is the amount of oxygen. So that's going to be my first step. So when I subtract these, I get 3.70 grams of O. We are going to now start with our grams of oxygen, because we can't go from grams of the metal to moles of the metal because we don't have the molar mass. That's what we're trying to find. We're trying to find the molar mass of this element. So I'm going to start with my 3.70 grams of oxygen, and I need to get to moles of this element. So I have 3.70 grams of oxygen, and in this I have, for every 1 mole of oxygen, I have 15.999 grams of oxygen. From here, I'm going to go to moles of M, because even though we don't have the molar mass, we still have a mole ratio. We have a full compound. So for every 1 mole of MO2, I have 1 mole of M and 2 moles of oxygen. So I'm going to take this part and put it here. So for every 2 moles of oxygen, I have 1 mole of a metal M. And now that I have this, I'm going to plug that in, which gets me 0.150 moles of a metal. And it's asking us for the molar mass, right? The formula for molar mass is equal to grams over moles, right? When we see it, we see G/MOL. So to find it, I'm going to take these moles in the amount of the sample of metal, and I'm going to plug it in to this formula, which gets, I'm going to do 11.17 grams of this metal over the 0.150 moles of M, which will get me 74.4 grams per mole, which I need to copy over here. I think the closest element might be, just to be curious, I think that would be arsenic, because that's the only one with a 74 on it. So estimated wise, that's probably the closest. That isn't asked, but it's nice to check. All right. Empirical formula. So we have a 2.00 gram sample of lithium, and we have a resulting 4.31 grams of some sort of lithium oxide. So if I subtract this 4.31 grams minus the 2.00 in the same way I did up here, I will get just the oxygen, which is 2.31 grams of just oxygen. Now I get to plug it into that fun little problem solving that is empirical formula. So I take these 2.00 grams of lithium and I convert that into moles, and then I take the 2.31 grams of oxygen and convert that into moles using their molar masses. So we're converting into moles, so I get to automatically put moles like this. The molar mass of lithium is 6.941. grams, and oxygen is 15.999 grams. This gets us 0.144 moles of oxygen and 0.288 moles of lithium. We divide by something. We divide by the smallest number between the two, which is oxygen. So both are going to be divided by 0.144, which gets us 2 and 1. Meaning, since these are both whole numbers, I get to put this directly into formula, meaning our final is Li2O, which we can double check because this is an ionic compound. The charge on lithium is 1 plus, oxygen is 2 minus. When we crisscross, we get lithium 2O1, which we can just make a 2, or sorry, a 1. You cannot just do that, unfortunately. You do have to show the math, otherwise it's not an empirical formula problem. You are more than likely going to get one that is of covalent bonds, so non-metals, because you can't double check it in that way. That's, especially if you have bone S, that seems a lot more likely, unfortunately. Yeah, all right. Number 8 asks, I'm going to highlight, a 3.750 gram sample of a compound contains only carbon, hydrogen, and oxygen. It is burned in a combustion chamber. The mass of the carbon dioxide produced is 10.05 grams, and the mass of water produced is 2.470 grams. What is the empirical formula of the phenol? All right, so we need to first find our grams of carbon and our grams of hydrogen. I don't want to find oxygen because it's in both of the compounds, so I want to focus on the element that's specific to only the carbon dioxide and only the water. So we have 10.05 grams of CO2 and I have 2.470 grams of H2O. I have to get from grams of CO2 to moles of CO2 because we always need to get to moles. Our ending is in moles of carbon. Sorry, our ending is in grams of carbon because we want this to be in carbon, or in samples, in mass samples, so it's ending in grams of carbon. So I go to moles of carbon, ending in grams of carbon using the molar mass. Same thing with the H2O, except we're going from grams of H2O to moles of H2O to moles of H to grams of H. So when I do this, the molar mass of carbon dioxide, we have 12.01, and we have 2 oxygens, which is 15.999, getting us 14.01 grams per mole. Sorry, 44, not 14. 44.01 grams per mole, which I will put down here. In 1 mole of CO2, how many moles of carbon are there? We've got an invisible 1 here, right? So I have 1 mole of carbon. And the molar mass of just carbon is, for every 1 mole, I've got 12.01 grams. It's technically 12.001, 0.011. 12.01 is fine. When I do the math, I get 0.2284 moles of carbon. I'm going to clear this now for space. Moles of carbon. Sorry, not moles. So when I get to here, I end with 2.743 grams of just carbon. On this one, the molar mass of water is 18.02 grams for every 1 mole of water. And then in 1 mole of water, we're going to hydrogen, right? How many hydrogens are there? I've got 2. And then molar mass of hydrogen, for every 1 mole of hydrogen, we have 1.008 grams. And that gets us to 0.2763 grams of hydrogen. And finally, since I have a total of 3.750 grams, I'm going to take the 3.750 and subtract the 2.743 and the 0.2763, resulting in 0.3713 grams. However, because the rest of these have only 3 decimal places, I cut that out and it's just 731 grams of oxygen. So now that I have that, I'm going to convert all of these to moles. So I've got, starting with carbon, I have 2.743 grams of carbon, 1 mole for every 12.01 grams. I've got hydrogen, which we had 0.2763 grams of. And then the 0.731 grams of oxygen. So we have 0.2284 moles of carbon for every 0.2741 moles of hydrogen. And 0.0457 moles of oxygen. I'm going to divide all of these by the lowest number, which is this one. Where I get a 1, a 5, and a 6. Meaning the empirical formula is C5H6O. Hypothetically, and this is something you will definitely see, especially if you have Bradbury or Boness, you're going to see a multiplier of some kind. If this was instead 5.5, I would need to multiply all of these numbers by 2 to make this a whole number, making this 11, this is now 12, and this is now 2, making it C11H12O2. If this was instead 5.25, then I multiply everything by 4. If this was 0.3, I'd multiply by 3. The percent of aluminum in the compound Al2X3 is 18.56%. What is the molar mass of the element represented by X? This is unfortunately a tad bit of doozy. So let's assume, like how we do with empirical formulas, that we have a 100-gram sample with 18.56 grams of Al. And we're going to get to moles of X and do the same thing we did in this problem, where we have the grams and we're getting to moles, and we'll subtract the 100. It'd be 100 minus this to get how many grams of X, and we'll use that at the end for the molar mass. I spoke through that fast, but I'm going to walk through the whole problem. So we'll go from grams of Al to moles of Al to moles of X to then, that's it. So molar mass of aluminum is 26.982. For every 1 mole of aluminum. And the molar ratio, it says we have 2 aluminums for every 3 moles of X. So when I plug this in, I get 1.032 moles of X. And I'll do that same thing I did before, where I have 100 grams. That was our sample. That's why we assumed this to be this. That's our total minus the 18.56 grams, getting us 81.44 grams of X. So we'll plug this into that mass over moles as the mass, and the moles we just got here. So we'll be doing 81.44 grams over 1.032 moles, which gets us 78.91 grams per mole, which I will copy here. Let's try and find that one like we did with the last one. That was selenium, 78.971. This was 78.91, approximately pretty similar. We're out of math. Yippee! Okay, so it's a little bit of a table that we've got going on for this question. You will 100% see this exact thing on the exam with different elements. So we're starting with calcium 42. There's 42 isotopes. Element nuclear symbol. That is where you have the symbol in the middle, the mass on top, and the number of protons on the bottom. So, what is the symbol for calcium? Ca. Mass is given to us, that's 42. And the number of protons, if we go to our handy dandy periodic table, it's the big number, it's got 20. Number of neutrons, the formula for the mass of an atom is protons plus neutrons. So if I have the mass and I have protons, I can find the neutrons. So for this one, that is 42 minus 20, which gets us 22 neutrons. Electron configuration. This is where we follow the periodic table. So we've got 1s2, let me start by going, these are the S's. I'm going to highlight instead. These are the S's. These are the P's. These are the D's. You're not going to get into these in this course. All right. So we have 1s2. We travel over to 2p2. Calcium is down here, so we're going to do a little bit of traveling. So we did 1s2, now we're doing 2s2. From 2s2, we travel over to 2p6. Why is it 6? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. There's 6 in P. So that's why there's 6. From here, we get to 3s2. Three S2, we jump over to 3p6. Now that we've hit 3p6, we're over here, and we finish at 2s2 because that's where the calcium is. 4s2. And that is our complete electron configuration. This next question asks, what is the number of electrons in the third shell? Third shell is anything that has a 3 at the beginning. So I've got 3 here and a 3 here. The numbers pertaining to that, I've got a 2 and a 6. 2 plus 6 gets me a total of 8 electrons in the third shell. Lewis dot structure for calcium. First, we need to find how many valence electrons this one has. Calcium is in group 2A, so it's got 2 valence electrons. So we'll start by writing calcium, and then we'll do our valence electrons. There's 2. I'm going to put them here and here. Can you put them on top and bottom? Absolutely. Can you put them here and here? Sure. I'm going to do it like that because I think I like it that way. Number of valence electrons, it's how many dots I just did. There's 2 valence electrons in calcium 42. This next one's a little bit trickier because you aren't given anything except number of neutrons and number of electrons in the third shell. If you noticed, our last one had a full octet in that third shell. This one only has 7, meaning it didn't get past that third shell. There's only one element that has 7 valence electrons in the third shell. So if I count that out on my periodic table, I have, this is the third, so 1, 2, 3, 4, 5, 6, 7. That's chlorine. So I know my element over here is chlorine. I can fill in a couple things using that now. Cl is that symbol. 7 valence electrons. When I do Cl, I'm going to count 1, 2, 3, 4, 5, 6, and finally 7. And since there's 7 here, there's 7 dots. Number of valence electrons, I've got 7. We need to find the mass number so we can do this portion. I am given 18 neutrons and there's 17 protons. 18 plus 17 gets me 20. No, that gets me 35 AMU, making this chlorine 35. I'm going to put a 35 up here, and there are 17 protons, making that our element nuclear symbol. For electron configuration, we're going to follow our same steps. 1s2. We've got 2s2. Then we've got 2p2. 3s2. And then finally, we're ending right here at 3p7. 3p5, which totals these two to 7, which checks the number of electrons in the third shell. All right, nuclear symbol for an iron atom that has 86 subatomic particles, and it's an atom, meaning it's neutral. So I've got I'm gonna make my little table with P plus, E minus, and N0, and not, whatever. It's iron, right? So that means I automatically have 26 protons and 26 electrons because it's neutral. 86 minus 26 minus 26 to get us just the neutrons, because your subatomic particles is the combination of these three. So 86 gets us 34 neutrons. So we have a mass of 60 because we add back one of the 26s. So I guess we could have just done this to get just the protons and the neutrons. It gets us a mass of 60. So when we write our nuclear symbol, we've got Fe in the middle, a mass of 60, and iron has 26 protons. Which of the following has the largest atomic radius? All right. So atomic radius, let me clear this, tends to go in this direction. The further down that way, it gets bigger. So whatever's further out that way is going to have the larger atomic radius. Na is here, Cl is here. Na is going to have the larger atomic radius because it is further to the left, because they're on the same plane. Next, it's asking between iodine and fluorine. Fluorine is going to be the smallest out of these, so iodine has to be bigger. Iodine is the answer for that one. Ionization energy is the exact opposite. So I literally just flip the side of my arrow. Magnesium and sulfur, I've got magnesium here, sulfur here. This one is a lot closer to the point of that arrow, right? So sulfur is going to have the higher ionization energy. Between nitrogen and arsenic, I've got nitrogen here, arsenic here. This nitrogen is a lot closer to the arrow, making our answer nitrogen. Electronegativity, follows the same exact trend. It gets more electronegative as it gets to fluorine, and it gets less as it goes to francium, all the way over here. So we're going between aluminum and chlorine. Chlorine's over here, aluminum's here. Chlorine is closer to the point of that arrow, meaning it's going to be chlorine. Between fluorine and iodine, fluorine will always have the highest out of anything ever. Lewis dot structures for single elements. So we have selenium, Se. It is in group 6, meaning it has 6 valence electrons. So we're going to do Se and then count out 1, 2, 3, 4, 5, and 6. Could I put in those 2 last dots over here? Yeah. Could I put them opposite? Sure. It does not matter. As long as you've got 1 on each side before giving out seconds, because everyone needs to eat before you start getting seconds, then you are absolutely fine. Silicone is over here, same area as carbon, which means it has 4 valence electrons. So when we do silicone, we're doing 1, 2, 3, 4, and that's it. There's no other option for that one because of that. Next up, we are doing electron configuration again. So let me re-annotate this real quick. So we've got S, P, and D. I do want to remind that while these two follow the period, D is a little bit special, and it is the period minus 1 for the number. So it's like number D and then a number up here. This one is the period minus 1, only for D. And for F, which we don't have to get into for germanium. If we were to get into it, F is period minus 2 for F. Okay, so let's get into this. I'm gonna do something crazy, guys. Oh yeah, okay. So for germanium, we are starting with S2. I'm a faker, OMG. This is part of S. So I've got 1s2, 2s2, 2p6, and then I've got 3s2, 3p6. Now we are over at 4s2. It's okay, I'll run off the edge a little bit. Now it gets a little special. We've got this whole thing, which is period minus 1, which is going to make it a 3, because we were in period 4. D, and count how many elements. You got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 3D 10. And then we end here at germanium at SP, sorry, not SP, 4P2, because I've got 2 before I hit that element. And we can see how many valence electrons this has because I've got our largest, our highest energy is 4. I've got 2 and 2, making 4 valence electrons, which makes sense because it's in group 4 with carbon. So that is the electron configuration. orbital notation for bromine. I'm going to start by first doing the electron configuration. So I guess I gotta reopen it like this. Okay. So, bromine, I'm going to leave gaps to allow me to have space to do the orbital notation. I'm gonna first highlight bromine actually. Br way down over here. So I've got one S2, two S2, two P6, three S2, three P6, four S2, three D10 because it's the period -1, and then 1, 2, 3, 4, 5. I've got 4P5. So I'm gonna space this out a little bit more like I told myself I would. Okay. So I've got a box for one S2. It's full. This one's full. This has 6, meaning I need 3 boxes because a pair goes in each one. One always goes up and one always goes down because you don't want them to collide. Technically, I'm supposed to be doing it like this. I gotta get that right. All right. Then we end with 4P5. Oh, those are bad. Okay. And that is your electron orbital notation. You just go up and down and up and down and up and down, and then you have it all. Up and down. Ionic or covalent. All you need to ask yourself is, does it have a metal? If it does, it's ionic. If it doesn't, ask yourself, does it have a polyatomic? If it does, it's ionic. If it doesn't, then you can assume it's a covalent compound. So, aluminum, is that a metal? Yes, it is. You've heard of aluminum foil. It's that one super cheap shiny thing that you've got going at home. So this is ionic. Is bromine a metal? No. Nothing ever ends with a metal. This is covalent. And that is the end of your exam.